Attending this CppCon, you will be at a level which you haven't experienced and which you haven't ever have thought of. You'll come to learn about many things which haven't been exposed to you before. So I'm sure you would love to be here, and once you experience this, you'll be like, I want to come next time, and you'll not miss this again.
All right. It working? Yeah. We can start. So you can come closer if you want to see slides or to see me better. Thank you for joining me today. And let's talk a little bit about performance of pseudo expected and monadic operations, or this abstraction. Let me introduce myself first. My name is Vitaly, and I worked at Remarkable. Remarkable is a Norwegian company, and we are doing this absolutely amazing ink notepads. So on this screen, you can see our latest model that we released like a few weeks ago. Amazing stuff. You can check it out. So at this company, I'm working at the App Foundation team as a principal software engineer, and our team is providing some libraries and frameworks for other team, but not contributing into the user-facing features. For today, at the very beginning, I thought to talk only about expected and the performance of monadic operations of expected. But then, when I started, I realized that it doesn't make too much sense when it's hanging in vacuum. It's too abstract. So that's the reason why we not only look into the monadic operations and expected, but also compare it with the closest competitor. And bear with me, I'll tell you why. So we will start with error handling in general, because if you use expected, exceptions, or similar stuff, I assume you need error handling or handling unexpected situations in general. Then we'll talk very briefly about expression expected, look under the hood of expecting monadic operations to realize what can have performance impact and what should not have performance impact and similar things. So then I have a few benchmarks for you. I'll put it here. I do not like the synthetic benchmarks, but there are some interesting things and I made some interesting observations, so I'm going to share them with you. And at the very end, I have very few practical recommendations on what you can change to potentially make it slightly faster or do less list allocations. So let's start with error handling in general. And my first question to you, are you familiar more or less with all of these cases of error handling methods like return, Scott, and I don't have to read it, you can do that. So very cool. I made this talk a few years ago at another conference. I will share slides, you don't need to make a photo, so that just for you, for convenience. So this is about different error handling methods, and if your knowledge in this area a little bit rusty, so just please have a look. And in general, I want to invite you to visit our Norwegian NDC Tech Town conference, then hosted nearby Oslo. That's a nice event. So now, what and why? I'm going to compare kind of exceptions and pseudo expected, because those two methods provide similar flexibility. You have an issue and you need to know what happened, not only that the issue happened. Then the similar use cases, nearly, I will show you. There are some code snippets. And then those two I can consider as the closest alternative in general. I know that can be a silly question, but are you familiar with exceptions, guys? Very cool. So very briefly, 3 slides, just to refresh stuff. So what the exception is, that's when you have an unplanned event that occurred during a program execution, and you create a certain object of exception type. Then we hand this object over to the system runtime with throw instruction. Then the runtime looking for this certain handler for it. And then if we match handler in catch block, then we're good. And if you don't, then we are not so good. That would be termination handler, and most likely your program crash after that. There are 4 cases for exception safety. I'm not going to talk much about it. But the first one is when we have no exceptions, some other error handling methods. Then we have strong exception guarantee. It's very close to transactional stuff, and you can roll everything back. Then the basic one, the basic is kind of interesting. Right? Imagine that you had, I'm not sure what, like a document or something, and you edited this document, and then something wrong happened. You have like your program, it's running, it's in a good state, but you lost all your data. So that's what the basic exception guarantee is about. That's the most common one, I guess. And no exception safety, that's bad. Everything can happen. So we are not going to be there. So this very small example of the exceptions. Vector of 3 elements, and we are trying to access the 4th element here, but assuming that it's 3rd element. So in this case, add will throw an exception. And I guess I tested it with GCC so that you can see an error like this. How can we throw an exception? How it works? You just, for instance, this element by index method, or pretty close to it, we check if we are in a range. If we are out of range, we throw an exception. Otherwise, we use the square brackets operator to get the element. That's it about exceptions. Let's talk about expected. Another question, so it's much less widespread. So are you guys familiar with expected? Please don't lower your hand yet. Have you ever used it in your production code? Okay, good. Thank you. So then this is a very basic example of standard library expected. So no custom delimitation or something. We have an expected box. I use this notation, so you can imagine this expected stuff as a box where you put something and then you can process it more or less common way. We put 42 here, then we just bring the value. We use expected as the same as exceptions when an operation can fail, and we need to know why this operation fails. So this not just not as an optional that simply carries if the presence or absence of object, but there is some data, like here, for instance, we have widget error, right? And from this error, we can understand what happened to widget. If an error, we use this unexpected to distinguish what the error and what the value, because you can have the same type for standard library expected for value and for error. And if everything is right, we just return a widget here. If we need to work with expected, we can use regular methods, regular ifs. And we can, for instance, check if there is a value. If there is a value, we're working with this. If there is an error, we do something else. We handle it somehow. Then there is more robust way of doing pretty much the same. So we get in widget, and then there are monadic operations to do similar actions. If everything is fine, that we invoke this function that accepts the widget as a parameter. So, and then we can do something with the widget. We can also invoke transform, for instance. This function cannot potentially fail. We only change the type, or doing something with an object. It's not necessary have to change the type. So, and or else is to just recover from error or just add some metadata or doing something when we are in an error state. We have 4 monadic operations. The regular transform that can change the type of the value or just adjust the object, and transform error, do the same for error, and then an or else, where you can not only change the type, but only return unexpected object if the operation fails. And the same for or else. Here I put slightly different stuff. So that stands for that you can change the type of value here, but not the type of error, because there are risks to lost your error. And this vice versa from or else. I'm not going to talk a lot about the exceptions themselves. Last year, here I gave a talk about monadic operations in modern C++, and mostly about practicalities of how can we use it, what the caveats and so on. This talk is already released on YouTube, so you can just go there and watch. That's the reason why I'm not talking a lot about monadic operations themselves and how to use them. However, the stood expected has some rather important implementation details that potentially affects the performance of using this type. So first of all, let's have a look on the types we have. There are 3 types. One type for unexpected, you seen briefly. That's a type that used as a wrapper or as a tag to distinguish between whether we have an error or a value. So not surprisingly, we have expected here. So technically, our exception can throw an exception. It's a little bit inconsistent. But anyway, so and then we have expected itself of the T and E. The T stands for the value and E for an error. Under the hood of stood expected, we have the following data structure. So this one, I believe, is copied directly from the standard, and it's implemented nearly like this in GCC standard library, if I'm not mistaken. So we have a union of value and annex. Annex that for an error, unexpected. So, and not that it's not unexpected of E, right? So that's the reason why you can have the same type of both value and an error. And most important right now, we have this Boolean flag has value that we have to carry around and that we're gonna check every monadic operations. So, which can already tell you that there will be at least one if per monadic operation. There is a simplified version of and then. So you can see that here we have at least 2 potentially problematic places. So we have one if, as I said, that always checks for value sign. So, and the second one, if there is no value, if there is an error, we wrap our unexpected into the return type. Then we deduced based on the function return type that should be expected of T on some T and the same error. And then we send it further on the chain. So here already you can see that we need to do one if check at least, and we have potential copy or move operation on the unexpected value. If you look at the transform operation, that's again simplified version. We have much more static or types check in the real implementation, but it looks super close. So we have this U type, that the function return type, and then we have expected, so that should wrap in this type because you can remap type, but you cannot change error type. And if there is an error, you have to carry it further. So, and it's pretty much the same as and then. So you first have to check the value, the same issue, and then you have to return your value also wrapped in the return type. Now, or else it's just the mirrored and then, in a sense. You just need to check this. If there is a value, then you just simply return this value further. You do not invoke the error handler at all. But you still need to check this sign of the value, and you need to wrap your return value into this type stand U here. For the transform error, this mirror transform pretty much. So we first check if there is a value. If there is a value, we just pass it further on our monadic chain. And if there is an error, we just invoke the handler and go further. So what kind of potential issues do we have here? We have obviously always have to check what that has value at every step. So we have if instruction inside of each and every operation. And we have potentially copies of value and error, because just imagine what if your type does not support move operations. So, or if it supports only move operations, that also gives some, well, I would say constraints for the entire monadic chain you have. And then result type. Result type can be completely different. And it also means that we not always can do proper elisions or proper return value optimizations, or not we, but compiler. So it prevents it from it. So now, since we looked under the hood to the both, okay, we haven't looked under the hood to exceptions, to be honest, and we're not going to do that here, but we just looked a little bit how it works. Both competitors, let's call it this way. Now let's compare the implementation. I have the very simple function square root here. So, and you might see that those two functions are nearly identical. On the left-hand side here, if the value is negative, we just, assuming we cannot handle other cases, but the value is negative, we just throw that the argument is invalid. Otherwise, we just call standard square root. Here, by the way, please note that many of the expected functions here, they're marked as no except on purpose. So, and the result type here should be expected of something. So I have expected of double and stood string because I use strings as an error. In real code, you most likely will be using separate error type, at least per library, if like per component, for instance, depends on how you handle the errors. So then we just simply create student expected if it's negative and calculate square root if everything is fine, if we can do that. How do we compute? How do we use it? I mean, we can use it different way, but I just put it right here. So if we have regular code without expected, we can use it like this. So log, then square root, then log. Just imagine that we have all other functions like log and so on that follows the same notation because to compose monadic functions right here, so log and then square root and then log, you need all of them to return the same, or like not the same, but convertible expected types. Otherwise, you cannot chain. What you also should notice that there are at least two hidden ifs here. So we first create the object in log function. Then we check if there is a value on or there is an error. Unconditionally, we always check it, as we've seen from the implementation. So then we invoke square root, and then we also check again if there is an error or there is a value, and then we invoke log. So two hidden ifs. How do we handle all of this, like errors if anything goes wrong? So those also like pretty much goes. Here I want to add that we are not using like monadic operations here or something else. Imagine that you kind of live in this middleware space where you already cannot use monadic operations anymore, cannot use functional code anymore. For example, you enter an UI domain, right? And your UI framework is not declarative and cannot work nicely with expected objects. You need to convert your error to something. You need to print it. You need to do something like this. One of the probably most famous UI frameworks for CPP is Qt. So, and if you want to integrate your logic, the backend implementation with the UI written in QML, you just do not have the good abstraction around to say, okay, fine, I return from this operation something expected convertible, and then please handle it. Furthermore, the UI engineers, they usually handle errors completely different way. So that's why in this particular examples, we just handle it's like it's a final handle. So say we do print line or we do login. And on the left-hand side, we just catch the argument and print something. And here we do not use monadic operations. We just take if there is a value, we print it. If there is an error, we also print it. So if, say, if it's UI up, it will be printed in the log, and you or an engineer or a user will see it. Now, since we are talking about performance, I have some reference data, let's call it this way. So here, you don't really need to read it, even if you can read it, but I will better version on the next slide. So here, for instance, you have right branch of if, you just compare, so it's logarithmically scale. So here you have at the first right branch of if, on the second row you have wrong branch of if, that's a misprediction. And then on the very bottom, you have stood exception, then thrown and caught altogether. It's like only thread context switch slower than this one. Now just please try to calculate. I'm not going to do that, too complicated. How many ifs, even mispredicted ifs, you can do for only single exception thrown and caught in your program. Again, we are talking about just regular exceptions, no optimization, no something like that. And we're talking about just regular monadic operations and regular expected. It turns out you can do a lot of monadic operations in comparison to the only one exception thrown and caught. There is a rather old paper here, why exceptions can be that slow. So I'm not gonna watch or spend too much time on it. You can just navigate and read. And I know that some implementations fixed many of the issue, but I doubt that those I put on the slide are fixed. So basically exceptions are allocated in dynamic memory, most likely. So, and then you need to use global synchronization primitives for this. And those probably two things that make even presence of the exceptions much slower, even because exceptions are known for this kind of zero cost abstractions, right? If it's not thrown, there is nothing. But I mean, there is something, right? And it's a little bit affects synthetic benchmarks. I will show you in the next few slides. Now it's time to do some benchmarks. And this doesn't mean that I will not show you benchmarks. I just want to encourage you, if you have any kind of good use cases or you have your own programs, please do your own benchmark and do it with a certain build type. Just have your build type set in release, or release with a debug info mode, because if you say measure anything in just debug, I assume you do not give the debug builds to the end customers. So that doesn't make much sense unless you really know what you're doing. So then use obviously your toolchain that close to production. If you have custom hardware, you should use this one as well. So, and then data types are also important. I will show you some cases and how data type can affect the performance, but basically you saw the second red circle on my slides, and that's where you return your type, and it's not easy to move or to copy. That can affect badly. Then you can have different number of elements, different number of operations, and this also affects performance. So yeah, I would just want to encourage you to do your own benchmark, and specifically if you work on embedded something, like for instance, we're doing these small devices, and when we test something on the desktop emulator, which is much faster, but the performance results are completely different because hardware works differently. There is screen, there is less memory, and the devices in general is much slower. This is hardware config of my old home machine where I did benchmarks. So probably don't even need to read through it or memorize some, or I mean, if you're expert and time and everything tells anything to you, this is just the data. So how to compare and what to compare? First of all, we should pick relatively light operations. And by light operations, I mean that the operations that doesn't take significant amount of time in comparison to either branching or expedition or something. Just imagine that we, for instance, in the reference operation, that what we measure, we decide to take I/O operation. We just write one symbol on the disk and read something from disk. So that means that we will measure performance of this operation, not of monadics or something like this. And we get absolutely similar results, I'm afraid, for all of the data. So yeah, I'm going to perform several operations in sequence. So that's a large step, but it's more than enough. So 10, 100, 1000, and 10K operations, these small light operations. We first run without errors, like no errors occurred. So we just run 10, 100, 10K operations in a row to see the results. Then there are three the most common use cases. So the first use cases, we have an error that occurred at the very beginning of the chain. If we either have the monadic chain right on the first operation and then failed, or we have something failed in the very middle, and then we can something fail in the very end of this computation chain, or if you throw exception at the very end. So the difference here is that we have certain operations performed normally, light operations, and then we have other operations skipped. So it's either always or else handler invoked, but we don't have it. So it's just we pass an error to the end. And we'll see how it affects the things. And we check expected at the end, or we catch in an exception. I test the result code, the assembly, so nothing is optimized out. We are quite good here. Let's have a look at the operation code. That's super simple and super trivial. On the left hand side, you have the operation with exceptions. On the right hand side, with expected. And of course, on the bottom part of the slide, the code I haven't wrote manually. I just generated a lot of code because imagine that you have like 10K operations and so on. So it's a generated code. Here we just what the data object, by the way. Data object is super small object. It does two ints pretty much, one counter and another object where we see whether there's a wrong step. So we can just emulate that the error occurred at the very beginning, in the middle, and then the very end. Small object that shouldn't really count here, or shouldn't create huge influence. So if there's wrong step, we throw something. On the right-hand side, if there is a wrong step, we return something, or otherwise we increase counter, that's just plus operation, so that the lightest one, and then we return an object. So here that the number of operation generated, like we do the results, we do operation, then we move on to new, move on to new, move on to new, and so on. That would be pretty much the same with what we have on the right-hand side. And here the number of and then is generated. Pretty similar. So we have the first operation, and then we chain the number of the same and thens of the same operation. Why I decided to do it this way, I have to explain, because this is super close to the real declarative design. Here I'm using words like declarative and functional as a synonyms. It's not quite right, but for this particular token, for this particular example, that's super synonymical. We have n monadic operations. Like imagine that in the real program, the design this way, you can have hundreds, thousands of monadic operations composed in different chains. And then if something wrong is happening, your exception, or not exception, expected object will be bubbled up to the handler. And this handler is usually located to, like, I would say, very close to what we can call system error handler. So, and the same is happening for the try catch. So we catch an error, and most likely we will not do transactional rollback. So this exception will be caught somewhere to, like, to the very close to the common handler for the all errors. Yeah, that's why we have, again, n monadic operations for one throw and catch instruction. That's we have first chart when we just run without errors. I need to say that both axes are logarithmically scaled because we don't have that many points. So that just please bear this in mind while you look in the charts. So, and this we have time in nanoseconds. I was too lazy to convert it. Cage does it by default and in nanoseconds. Then we have a number of calls here. So, and if there are no errors, you can see that the more operations we perform, the slower the computation chain is. Makes sense. But try-catch is like slightly slower here. Even if just, please consider that we have the number like even here, the very here, we can like 10K of extra if checks. So, and when we perform the operation without it, but there is only try-catch in the program, so it's slower, at least in my benchmarks. So you can have different results. When the error happening at the very beginning, so that's growing pretty much the same, like linearly, but at the same time you can see that the effect of when we actually throw an exception and catch it, it's significant. So we just throw it at the very beginning, right, of the computation chain, and just forward it to all of these handlers. So you can see that the data is more or less correct. So we have this 5,000 and most, and on the previous chart we have like 10K nanoseconds. So, oh, sorry. This was different stuff. So yeah, here we have like 50K, and here we have like 5K. So we do not really perform computations in both cases. We just, at the very first operation, we either raise an exception or we just return unexpected. And then all other nearly 10K operations, they are not performed at all. And that kind of data we have when the exception thrown at the very beginning, or when our unexpected created is also at the very beginning. That's another interesting case. And with this case, we have an error that occurred somewhere in the middle of computation chain. So what does it mean? That we have, for instance, here 10 operations, right? And the error occurred, exception thrown or unexpected object created, and the 5th operation. So we do 5 operations, and then for other 5 operations, for expected, for instance, we just goes to the else alternative branch of if we don't do any computations. And obviously for expected, they are object just handed over to the system runtime, and it ends up in the handler. So, and from this chart, you can see like then the more objects we have in computation chain, that the closest the lines are. So for like, if you have 10K operations and they're somewhere in the middle, all of this, and perhaps the right side, the operations where you check alternatives, that's creates some, extra time or extra burden for the entire computation pipeline. And if we have it at the very end, so you see that they start converging at the much more earlier, right, than before. So at the very end, we have like pretty much situation when no exception occurred at all, or like when we just have the computation without unexpected cases. Any questions on those charts? Super synthetic, quite far from reality, but still, shoot.
Why did you choose to vary the Y scales by so much? Like it goes from 0 to 500, and there's a big jump between 1 and 5,000, and another really big jump from 10,000 to 50,000. Is it difficult to make the correlation between them?
Yeah, I would tell that I just say my script to please use log scale for both axes, and that's it. So I didn't choose the intervals, how they scaled. Because that, if you start doing from this chart, you can, make some conclusions at least. So how it works. And the numbers themselves are not super important. That's what important is, that you can compare, for reference, as a top-notch number, so that the sum operations were performed or not performed. So this you can just visually compare. Again, for the real cases, you might have the charts can be completely different. And what you need to do is just, if you want to measure, replace either the entire class, entire component, entire library for the exceptions to expected, and then profile. So it will not be enough to say replace only single function or start using expected in scope of only one function. Depending on your function, but I hope you don't have a function like of 1,000 operations or something like this. So very good. I have some general conclusions here. And I mean, from my synthetic benchmarks, with these very light operations, I can conclude that the code with monadic operations is slightly faster than the code with exceptions. Again, you might have completely different data. So then if an error happens at the very beginning of calculations, then in my examples, monadic operations are significantly faster because we have on one side the event of exception that's thrown in code. On the other hand, we have absolutely nice branch prediction where it's always the alternative branch. So we do not invoke handlers at all. And for the call chain, if we have approximately less than 500 operations on chain, and by chain here, I mean not only one chain, like assume you, for instance, retrieve a widget that do something with the widget, change its ID, then render it, for instance, and then return or handle error code. So I assume like the entire chain of computations. Imagine that you, for instance, not only created a widget, but you also put it somewhere visually on the layout, then you reposition it and so on. And if we count all of these operations as a single big pipeline, then we have the better picture probably, because that's how it works with exceptions as well. So we count all operations before we initiate an event, for instance, widget creation event, and until something goes wrong. And this is a very valid and very interesting question. So you saw probably that the second problem, second large circle, is extra copy or move. What do we do with extra copy and move operations? And I will show you, I will start with a very simple example. I have my noisy object. If you're not familiar with noisy object, it's the object that adds prints for the events of construction, copying, moving, destruction, and so on, for all of these major 5 things. I have expected of noisy and string. I have my operation, does nothing. It just creates noisy. And we assign it to something. What you can see from the right-hand side, that we create noisy, then we move it out. So if you think from CPP11, this would be by default. So it comes with move semantic. So it's moved. And then we have destructor for the something created, and then destructor from something that was moved. We have actually a way to slightly reduce the influence of this, but I will not going to show it you right now. That would be in the next section. Now let's look at the and then or transform operation, because that would be pretty much the same. So we have the function, again, with noisy. Assume we created our result somewhere, and then we store it as a value. It's a regular value, not a temporary value, just a value. So our do something function also does something very important. It prints. So then we do something with noisy, see, then we return it. Then it hits copy constructor, that we return it once again from the operation. It hits copy constructor again, and then it hits 2 destructors. So you see we copy at least twice, and we destroy it twice. So any suggestions what can we do to do not copy? Yeah, that's a very good stuff. You can, I heard move. A naive approach, right? Can we just move? I put my R value reference here. So, and I got compilation error. Guess why? Correct. So the answer was what you can see on the slide. So you can either should have already a temporary object, or you can explicitly move it. Otherwise, the correct and then will not be invoked. It will not be compiled at all. So now, from what you can see, that we do something, then we move, then we do something, then we move, and then two destructors invoked on the pretty much empty moved out object, which is very nice. In most of the cases, you will get this situation by default and for free. Why? Because your result object is returned from some function, right? So it's already temporary. That you can already invoke handlers like this. But just beware that you have object stored somewhere. Just stored to the const object specifically. Please don't do it. Just move it and process like this. So then you can save some copies in a good way. So now, what I did, I have another result here, and another result is just rebinds things around. So I have error is my value right now, and I have noisy object as an error. So I create an error somehow of noisy object, assign it to result, then I move result, and then see, like, it doesn't really matter what I have here in these handlers, like by value, by reference, by something. Those handlers will never be invoked because we have an error, right? It's alternative branch of your if. So none of those three handlers is invoked. And for noisy, we have, like, see how the error carried move, move, move. It's explicitly move, just because your result is a temporary object, which is very good. Conclusions here, like very intermediate. So copy move operations for value will be performed on each step of monadic operations, and extremely unlikely they will be optimized out, because how? You saw the implementations, and I mean, perhaps some compilers can do that, I trust it, but most likely they will not be optimized. Then let's start with very few practical recommendations. And let's get back to the case of creation. How many of you are familiar with in-place or similar stuff? Not that many. I will just very briefly explain, because what in-place does, it's create an object like kind of very close to like placement new. So you have an object and you don't create an object first and then copy it inside of the result, but you create them all together, result and the object. So it is how in-place back working, for instance, and similar constructions. So my noisy object is, has a default constructor. That's why I don't have any arguments passed here. But if your object have any arguments, so you can just pass it as a variadic pack after the comma. I'm not sure how intuitive. For me, it sounds a little bit counterintuitive, to be honest. But to create the value, use in place. Fine, use it in many places. But to create an error, you do std unexpect. So just to make sure that you can create your result all together with an error and all together with a value. So for this, you need to use either unexpect for error or in place for the value. So then we use, you can see on the here, that's a constructor and destructor. So nothing else happened. And so like no move, no extra destructor for move it out object that we can use. Most likely, in many cases, you probably will not be using this. You will just return an object. And if you really need optimizations or this is important for you, then you can use in place. And which is the most important stuff, when you can do that, because most often your result is like already created object, already created complicated object that already came from some function, from some routine, from some calculations, and you don't really need to create it. It's already created for you. So that's why this, this good practical recommendation, but from my experience, there are, very few cases when you can really use it. And I guess the number of cases where you can really make an impact is even smaller. Still, it's here. So then what you can use is use smart pointers or references, right? Because if you have smart pointer, say unique pointer, it's already allocated once, it has pretty nice semantic, so it will be moved for you always. Or if you have shared pointer, it will be copied, but you know how shared pointer is copying, right? It's kind of shallow copy, and the price of this atomic variable that protects control block, pretty much it. So, and here, the expected itself and optional, they do not support references by default right now. I think there was a talk at CPP Now this year about references, and the shortened version of this talk is given by Steve, like I guess the next room right now. So you can just go here on the YouTube, found this talk, and see the proposals for references for optional. That's rather interesting. Last time's provoked many discussions, so we will see how it goes. But as of now, you're familiar with reference wrapper. You just need to invoke like not many hands, explain a little bit. So you use this stud column ref or stud column ref to wrap your object. That's pretty much thing that holds reference and has very close to value semantic. And this thing is simply copyable, movable, and so on. But at the same time, you can use method get, for instance, or pass to the function that accepts reference directly and use it as usual. And just beware that your object should have long enough lifetime. So this lifetime of the object should be the same as the lifetime of your computational pipeline. Usually it's okay for Monadics because you use this dot operator, right? And it's kind of prolonged lifetime, so should be fine. And I guess, yeah, I have one more recommendation for you. So use simple data structures for objects. It's like not noisy, but I'm not going to talk a lot about the standard layout, about this old-fashioned POD, stands for plain old data, and so on. But if your structure has, say, it's just structure, without like static fields, without arrays, without virtual inheritance, and so on, I mean, that would be like too strict to say it's trivially copyable, but it's very simple structure, so like data class, if you will. So then you most likely can pass it by value. In many cases, they will be nicely moved, and you don't need to care too much. With that, I guess, thank you guys. We are on time. I tried to set 15 minutes for questions aside. 12 minutes remain. So if you have anything to ask, please go to the mic, shoot. Or if you don't, we can just chat later. Yeah, please, the question here.
Right. Thank you for the talk. Can you go back to the fourth slide for the results of your benchmarks?
For which slide?
The fourth slide for your results benchmarking. I think it was like 47 or somewhere.
Okay, I will just scroll it. This one.
Right. You might have already mentioned it, and I might just have missed it, but I was thinking that try-catch is really good when you go along the good path, like there's no overhead. But looking at this, it seems like it performed worse. Do you know why that happened?
I do not know why it's happening. I tried to answer on the, where was this? On this slide. So, but basically you need to, first of all, check for yourself, like for your implementation standard library, for your system, for everything. So I do not have the really good answer why it's not that significantly slower, but it's slightly slower in my benchmarks.
At the 10,000 mark, 10,000 function calls, it seemed significant, like on the log scale.
It can be significant, but it's like all on the good path for the monadic operation. So that's always a right branch. So the branch predictor works pretty nicely. Yeah. This is like optimizing, absolutely amazing the modern machines. So, but again, I wouldn't trust synthetic benchmark at all. Not at all, but you can use it for some reference data, but still. Yeah, here we go.
All right, thank you.
Welcome.
Hey, thanks for the talk. Think maybe misunderstood some part of it, and I wanted to then expand on that. So when you were comparing the try-catch and the monadic operations, you said something about repeating the monadic operations a lot?
I can go back to what slide we have. No, not here. Okay, but doesn't really matter. This operation. So what we can do here is we generate the code, like of course with tooling, not manually. So that, for instance, here, if you have 10K operations, there would be 10K and then composed. And the same for regular operations. So 10K regular operations versus 10K monadic operations.
Right. And so then along with that, I wanted to know, did you try nesting the try-catches and see if there was a change in performance where there was, instead of just there being one try-catch in your entire operation, there was like a try-catch and a try-catch and a try-catch?
The answer is no, I didn't. Because I tried to get the benchmark for the simplest possible case, because there are many interesting cases to export, like the one you said. Then another one is like, say that the passing larger objects. So I have like probably 64-bit objects, depending on the architecture that I'm passing. But so what if I'm passing a tuple of 10 elements, for instance, how this would affect both of the cases? Because like 10 elements, okay, like too much probably, but tuple of 3 elements, it's a very common case when you do monadic composition. So many use cases, but the answer is many interesting things to learn about, but I tried to do like the simplest and the most general.
Right. So then when we look at the slide, we're looking at one try-catch versus 10,000 monadic operations.
Yes, it's exactly like this. So we just have n monadic operations, so because it's the closest case to the real one, and then we have only one try-catch. So yeah, cool.
If you have very different performance, depending on whether or not, as you just brought up, using a different object has better performance in a throw catch versus the monadic operations, would you choose to always take like the most optimal route, having different try catch versus expected throughout your code base, or would you choose one despite the fact that you're losing out some performance in some situation?
That's an interesting question, because like a larger object can affect potentially, but it also not always will affect, because in my example specific, it will not affect, because we have an operation, we return object out of it, and then we move the result, and that's what we do with the and then. However, what I meant under larger objects, that you can have a completely different program. So, and when you restructure your program from, say, exceptions to expected or optional, you can have completely different computation flow because you refactor in your code. And especially if you do not have a lot of experience with that, you can just start probably copying this object extra times when you don't really need it, and then you can have completely negative impact on performance. So that's what I meant, basically, that the larger object can affect the things. Any other questions? Yeah, if not, thank you guys. Have a nice evening.